In this video, we're going to just start to discuss the idea of light. So we've already learned about the properties of waves, and so we are going to review the properties of waves, and we're going to look at how light demonstrate waves properties in this unit. And the next unit in modern physics will actually talk about how we began to figure out that light also had particle properties. So there was a huge debate between whether or not light was a wave or a particle, and we'll look at experiments that showed that light was a wave, and we also look at it as light as a particle, and experiments that were done to prove that light was a particle. So light actually has wave-particle duality. Now, if we think back to when we studied waves, we had the frequency of the wave and we had the wavelength of the wave, and that was related by the wave equation, where frequency times wavelength is equal to the speed of the wave, or the velocity of the wave. So in this case, we use, instead of v, we use the letter c, because c actually stands for the speed of light. So what actually is light? When we looked at sound, sound is a mechanical wave that is transmitting energy through a medium. It required a medium, so it had to move through a liquid or a gas or a solid. But electromagnetic waves actually can move through the vacuum of space, and we call them radiation. And they're actually oscillating electric and magnetic fields. And we know from studying electricity that electric and magnetic fields are actually perpendicular to one another. Now, electromagnetic radiation in a vacuum always moves at the same velocity, which is the speed of light, 3 times 10 to the 8th meters per second. Now, that's in a vacuum. As light travels through other mediums, so we know it can pass through, glass and air, its velocity changes slightly. So this actually shows an example of the waves where you can see the magnetic and electric fields here. So you see that they're actually perpendicular to one another. So because of this, we can actually polarize light or use filters in order to eliminate waves that are in a certain plane, or isolate waves that are only in one plane. So this is done by a polarizing lens, and this is how a lot of sunglasses work, by using polarizing lenses. So they eliminate all of the waves except for whatever is in the plane. So you can see here, light is emitting waves that are oscillating really in every plane, and then a polarizing lens will allow only light in one plane to pass through. So if you use multiple polarizing lenses, you can actually eliminate all of the wavelengths of light. Now, just like when we talked about the idea of loudness and how it spreads out over, or intensity, and how it spreads out over a distance, it's the same idea for light. So this, we call it sort of the flashlight theory. If you were to shine light at a wall and you were to move backwards or spread that light over the wall, it would be less intense at any single point. And so there's these ideas of the rate of emission, so how much light is actually being produced, versus the rate of lighting, how much is illuminated. But don't worry too much about this. We're actually not going to perform any calculations, but it just helps you to think of that idea of light spreading out and being sort of circular. Okay. Now, this equation can be used, and it's very similar to the intensity equation, but I wouldn't even worry about this. I've never actually seen it used in the AP, and we won't use it in any classwork. All right, so the electromagnetic spectrum includes all sorts of electromagnetic waves. So visible light is only a very small range in the electromagnetic spectrum, going from wavelengths of about 400 to 700 nanometers. But all of these are examples of electromagnetic waves, and they just differ based on their wavelength or their frequency. So radio waves and microwaves and infrared waves are fairly large waves, and we typically think of them as helpful. We use them for things. Whereas on the other end of the spectrum, we have waves that are a lot smaller than visible light, so UV, X-rays, and gamma rays, and these tend to be potentially harmful. So we know that UV rays can actually cause skin cancer. X-rays, when you go to the doctor, you actually have to put like a lead blanket over your body when you're getting X-rays, and gamma rays are what are produced in really high energy nuclear reactions that can be cancer causing and fairly dangerous as well. So radio waves are very large waves, and they come in different bands, and based on the band that they come in determines whether or not you're going to be an AM or an FM. But remember, they're just very, very large electromagnetic waves. And TV waves are similar to this. Now, everything has really gone to digital now, but we used to be able to use antennas in order to pick up electromagnetic signals from the air like you do with your radio. Now, microwaves are a little bit smaller, and we can actually harness them in order to heat food, and that's how a microwave actually works. Now, cellular telephone waves, these are the same. They're a little bit smaller. They're right around the microwave range. And then infrared is right outside the spectrum of what we can see with our light. But there are other organisms who can actually see with their eyes light that's in the infrared range. It's just a little bit bigger of a wavelength than our eyes can actually detect. Infrared is also used with some different types of remote control sort of devices. Now, white light, like I said, is visible light, and it ranges from 400 to 700 nanometers, which is, the Roy G. Biv of the rainbow. And if you put all of the light together, all of the different colors together, it appears white. Okay, so hopefully that's all review. And actually, Isaac Newton was the one who proved this idea of by using the prisms to split the light. And we'll actually look at prisms later in this unit and talk about how shining light through glass causes the light to bend, and therefore we can actually see the different colors because of the different wavelengths. Okay, so here's an example of a prism from the Pink Floyd album. Now, when we look at light in this unit, we're going to treat it as having a starting point and ending point. So it's going to be like a ray or a vector. And this will come into play when we look at mirrors and lenses and determining how mirrors and lenses produce images. Now, on the other end of the spectrum, when we move past visible light, getting smaller is UV. And like I said, UV radiation, it's small enough that it can cause damage to your skin cells and actually lead to skin cancer. Whereas X-rays are even smaller, so they can penetrate through soft tissues, and that's why we can create an image with them, because they're so small they pass through sort of the skin and the fat, and they'll bounce off more dense tissue like your bone or even like dense cardiac muscle and things like that. And then finally, we have gamma radiation, which is the most dangerous of all, and this is what is used or produced during nuclear reactions, and it's very tiny, and it can cause cancer. All right, so that is just an intro to light and light as a wave and the electromagnetic spectrum.